Wrap a rope a few times around the fixed post, and one hand can hold a force that would take a truck to match. Dock workers do it every day, taming ships against the tide with a light grip. The secret is friction, curving around the drum. Let's derive exactly how it works. Here's the setup, seen from overhead. A rope wraps around a fixed drum of radius r, entering on one side and leaving on the other. On one end, a heavy load pulls with a large tension we'll call T sub A. On the other end, a sailor holds the rope with a much smaller tension, T sub B. Between rope and drum sits static friction with coefficient mu sub s. The sailor holds just hard enough that the rope is on the verge of slipping. Let theta sub BA be the total angle the rope sweeps around the drum. Our goal is to prove that T sub B equals T sub A times e to the minus mu sub s theta sub BA. Zoom in on a tiny slice of the rope, spanning a small angle delta theta, so its arc length is r times delta theta. Four forces act on it. The drum pushes outward with a normal force N. Because the load would drag the rope to the right, friction resists, pointing left with magnitude F sub s, and the rope's own tension pulls at each cut end. On the right, the tension T, on the left, T plus delta T. Since the sailor's side carries less load, the tension drops across the slice, so delta T is negative. Now resolve everything onto two axes, I hat pointing right and a j hat pointing radially outward. Each tension end tilts from the horizontal by half the slice angle, delta theta over 2. Along I hat, the right tension gives T cosine of delta theta over 2. The left tension pulls back with minus T plus delta T times cosine of delta theta over 2, and the friction subtracts F sub s. Along J hat, the normal force M points out. While both tension ends lean inward, each contributing minus is magnitude times sin of delta theta over 2. The slice is infinitesimally thin, so use the small angle approximations. Cosine of delta theta over 2 is essentially 1, and the sine of delta theta over 2 is essentially delta theta over 2. Take the I hat balance first. With cosine equal to 1, the two tension terms become T minus the quantity T plus delta T, and the T's cancel, leaving minus delta T. So the horizontal balance reads minus F sub s minus delta T. The slice is in static equilibrium. Nothing accelerates, so this sum is 0. Minus F sub s minus delta T equals 0. In words, the friction on the slice exactly equals the drop in tension across it. Now the j hat balance, replace each sine of delta theta over 2 by delta theta over 2. The two inward tension terms become minus T times delta theta over 2, and a minus T plus delta T times delta theta over 2. Add them, the normal force N minus T delta theta minus 1/2 delta T delta theta. That last term is a product of two tiny quantities, delta T and the delta theta, so it's far smaller than the rest, and we drop it. What remains is N minus T delta theta. Static equilibrium sets it to 0, so the normal force is N equals T times delta theta. The harder the rope pulls, the harder the drum presses back on that little slice. Here's the crucial link. The rope is on the verge of slipping, so static friction is maxed out at its ceiling. F sub s equals mu sub s times n. From the horizontal balance, friction equaled minus delta t, so minus delta t equals mu sub Sn. Substitute the normal force we just found, N equals T delta theta, and you get delta T equals minus mu sub S T delta theta. Divide both sides by delta theta. The ratio of the tension change to the angle change is minus mu sub S times T. Finally, shrink the slice to nothing. As delta theta goes to 0, that ratio becomes the derivative, dt by d theta. So dt by d theta equals minus mu sub s times t. The rate at which tension falls off is proportional to the tension itself, the signature of exponential decay. Solve this differential equation by separation of variables. Gather the tension on one side, the angle on the other. dt over t equals minus mu sub s d theta. Now integrate both ends. On the left, t runs from the load value t sub a, where the angle is 0, up to the Saylor's value t sub b, where the angle reaches theta sub ba. The integral of dt over t is the natural log of t, so the left side gives the natural log of t sub b over t sub a. On the right, mu sub s is constant, and the integral of d theta from 0 to theta sub ba is just theta sub ba, so the right side is minus mu sub s theta sub ba. Set them equal. The natural log of t sub b over t sub a equals minus mu sub s theta sub ba. Exponentiate both sides to undo the log, and the ratio t sub b over t sub a equals e to the minus mu sub s theta sub ba. Clear the fraction, and there it is. T sub b equals t sub a times e to the minus mu sub s theta sub ba. Put in numbers to feel the power of that exponential. Take a rope and pose friction coefficient of 0.2 and wrap the rope in 4 turns, each turn adding 2 pi radians of contact. With 1 turn, the holding fraction is e to the minus 0.4 pi, about 0.285, so the Sailor already needs under a third of the load. 2 turns square that effect. E to the minus 0.8 pi, about 0.081, roughly 1 part in 12. 3 turns e to the minus 1.2 pi, about 0.023, near 1 part in 43. So a load of 10,000 newtons over a ton of pull is held by barely 230 newtons, a firm two-handed grip. Every extra rep multiplies your advantage. That is what exponential decay buys you. Step back and see why this works. Friction doesn't act at a single point. It acts along every bit of rope touching the drum, and each bit shaves off a slice of tension. Because each slice removes a fixed fraction, not a fixed amount, the losses compound, and the tension collapses geometrically, rep after rep. That is the whole trick behind capstans, belaying devices, and the cleats on a sailboat. Let the curved surface do the gripping, and your hand only has to win the last tiny remainder. A rope, a post, and a bit of friction quietly multiply human strength. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.